Hey everyone, in this video we're going to go over curve sketching without the aid of a graphing calculator or computer algebra system. So we're just going to do everything by hand, algebraically, and using calculus. And this is sort of my list of steps to take. We want to state the domain, find all x and y intercepts of our function, find any asymptotes, whether they're vertical asymptotes, horizontal, or slanted asymptotes. And so these are things that from the beginning of the semester. So in this section, the curve sketching is kind of where everything comes together, right? Domain, x and y intercepts, vertical asymptotes that come from the domain, horizontal asymptotes, limits to infinity, or slanted asymptotes, which is also limits to infinity, but this is when the power in the numerator is larger than the power in the denominator. Find intervals where the function is increasing, decreasing, intervals where the function is concave up and down, and then finally sketch the graph of the function. So let's get started with this example. Let f of x be this. So first of all, what is the domain? So for the domain of the function, so I'm going to go over here. The domain, we have fractions. So that means we don't want, so we want to exclude everything that will make the denominator 0. We don't want the denominator to be 0. So exclude x values where or when x squared minus 1 is 0. So here factor, always try to factor rather than moving things to the other side and taking the square root, just because if you're the kind of person that forgets the plus or minus when you take square roots, then you don't want to make that mistake. So then here x equals -1 or x equals 1. So we're going to exclude those values. So our domain then is going to be minus infinity to -1, not included, so parentheses union -1 to 1, right? The only things we're excluding are -1 and 1. Sometimes a number line helps. If you put -1 and 1 there, those will be open circles and you will shade everything else. And then from 1 to infinity. So this is the domain. So then what's happening at -1 and 1? So we'll see that those are likely vertical asymptotes. They could be holes in the graph, but it kind of depends on what's happening in the numerator. So find x and y intercepts. So let me maybe label these. So 1, 2, 3, 4, 5, and 6. So the domain is 1. 2 is find your x and y intercepts. So how do you find x intercepts? You set y equal to 0 and solve. So our function is f of x equals 2x squared over x squared minus 1. So set y equal to 0, that means set f of x equal to 0. So you will have this equals 0. And a fraction is 0 when the numerator is 0. So that means that x is 0 is your x-intercept. And then what about y-intercept? To find the y-intercept, we set x equal to 0 and find y. So then you'll have 2 times 0 squared over 0 squared minus 1, but this just gives you 0 anyway. And so the x and y-intercept are 0, 0. And so now to the third thing, which is find all asymptotes, vertical, horizontal, or slanted. So how do you know if -1 and 1 are asymptotes instead of holes in the graph? And if it was a hole in the graph, that would mean that when I factor x minus 1 and x plus 1, then I will have the same factor up here. So if I had something like x times x minus 1, then as I cancel those, that will create a hole in the graph. But that doesn't happen here. So we don't have this situation. So that means that we have a vertical asymptote at each of those points. So we have vertical asymptotes. They come from the domain at x equals plus or minus 1. Do we have any horizontal asymptotes? How do you find horizontal asymptotes? You take the limit as x goes to plus or minus infinity. So let me start with the positive infinity of your function. 2x squared over x squared minus 1. Here, because they're both, the highest power is square on both, I can say plus or minus infinity here. So I'm going to have, and I can use our shortcuts from chapter 2 when we did limits. Powers are the same, so this is going to be 2. So we have a horizontal asymptote. I'm going to abbreviate it HA, just like we did back when we were doing infinite limits. So the horizontal asymptote is y equals, right? It's a horizontal line, so it's y equals 2. And here, these are vertical asymptotes, vertical lines, so x equals 1 and x equals negative 1. So we have our asymptotes. What's the fourth thing? Find the intervals where the function is increasing, decreasing, and then intervals where the function is concave up and concave down. So this is what we've been doing most recently. So for increasing and decreasing, we want to find critical numbers. So we want to set the derivative equal to 0 and find critical numbers, and then go through our number line or the chart with the intervals. So whichever method you are choosing to do, but you have to write on a quiz or a test, you have to show me how you're getting your intervals, whether it's the number line or the table of values. So let's look at our function. So f of x is 2x squared over x squared minus 1. So let's take the derivative. How do you find the first derivative? We have division, so let's use the quotient rule. By the way, normally I would already start the graph. It's just I'm limited on the space that I have here on my screen, but normally I will have perhaps the graph already started here and be writing the things that I have. So let me do that maybe here to indicate what I mean. So when I put my grid, right, so then I go for the domain, we just find the domain. But as soon as you find your x and y intercepts, it's a good idea to plot them. In this case, they were the same value. So I'm going to go and plot 0, 0 as my x and y intercept. And then I also found that I have vertical asymptotes at plus or minus 1, at x equals plus or minus 1, vertical asymptotes, and then a horizontal asymptote at y equals 2. So then I'm going to go over here to my negative 1 and 1 and draw my vertical asymptotes. So we have our vertical asymptotes and our horizontal asymptotes. And so that kind of gives us an idea of where our graph is going to land. And so now let's look at the intervals where our function is going to be increasing and decreasing, and let's continue to try to find the derivative. So for the derivative, we said we're going to use the quotient rule. So the quotient rule is the bottom times the derivative of the top. So times 4x minus the top, 2x squared, times the derivative of the bottom, which is 2x, all over the bottom square. And simplify as much as you can. So this is going to be 4x cubed minus 4x minus 4x cubed all over x squared minus 1 square. And continue simplifying until we can find our critical number. So now here, notice that my cubes cancel, and so we're left with just negative 4x over our x squared minus 1 quantity square. And now we can set this equal to 0. Now I am going to kind of box this up, as this is a good place for me to save, to use this to take the second derivative. So use this for f double prime, because this is a nice simplified way of keeping the derivative. But in order to find my critical numbers, I'm going to simplify just a slight step further. X squared minus 1 factors into x plus 1, x minus 1. We saw that when solving for the domain. So this is going to be x minus 1 squared then times x plus 1 squared, right? X squared minus 1 is x plus 1, x minus 1, the whole thing squared. So I can distribute this, but this helps me see my critical numbers better, because I know the derivative is 0 when the numerator is 0, which means when x is 0, and f prime is undefined when the denominator is 0. So that means when x is 1 and x is -1, which we could have already seen that from our domain. So we should have expected to see 1 and -1 show up as critical numbers. And so now those are critical numbers, and so let's go to the number line. And we'll place our critical numbers there, so -1, 0, and 1. And we're trying to see what is the derivative doing, first derivative. So we're using the first derivative test and trying to see what does that mean about the function. So pick a test point that is in the interval -infinity to -1 and see what our function does. So let's pick, what can we pick? X equals -2 and plug it into the first derivative. So f prime of -2 will be -4 times -2. So negative times a negative is positive over, and then notice that these, both of those are square. So regardless of what x value you put in here, when you square it, it's going to be what? Positive, right? So the bottom is always positive. So this is kind of neat to know, because we really just need to check the sign in the numerator. So everything is positive, so that the derivative here is positive, which when the derivative is positive, that tells you that the function is increasing. And by the way, the derivative here at -1 and at 1, it's undefined, and at 0, the derivative is 0. So we could, at 0, have either a local max, a local min, or a saddle. So let's move on to the next test point. Something between -1 and 0, you can pick -1/2, right? So then f prime of -1/2 will have -4 times -1/2, so negative times a negative, again, is positive, and the bottom is always positive because of that square. So this is going to be positive. So the first derivative is positive there, which means the function continues to increase. So -1 is not in the domain. So normally, if this was in the domain and we had the derivative was 0 there, this would indicate that you have a saddle, like x cubed. But -1 is not in the domain, so this doesn't tell us much. It's just, we know that it's increasing, but nothing is happening at -1 in terms of extrema. So we know from -infinity to -1, the function is increasing. So going back over here, so we know in here it's increasing, and then between -1 and 0, it's also increasing. So what does that look like? And then something between 0 and 1, pick +1/2. So then f prime of +1/2, now you're going to have -4 times +1/2. So negative times a positive is negative, and the bottom is always positive because of that square. So our derivative here is negative, right? Negative divided by positive is negative, which means that the function is decreasing. So what sort of a thing do we have at 0? You go from increasing to decreasing. So this is going to be a local max. That's where the local max occurs. To find what the maximum value there is, you have to plug in 0, which actually we know f of 0 is 0. Something between 1 and infinity, plug in 2, and so f prime of 2 is, so you're going to have a negative again, because -4 times +2 is going to be negative, divided by the bottom is always positive. So you're going to have the first derivative here is negative, which means that the function is decreasing. And we could have also used the shortcut that I have shown you before, that you pick just a test point. So like when I picked -2, I got everything is positive, and then just look at the powers. As I go across -1, which term did negative 1 come from? Negative 1 came from x plus 1, right? When you set that equal to 0, you get x equals negative 1. So it came from this term, x plus 1, which is square. So because the power is even, that means that whatever sign you had here is not going to change. So it stays the same. So as you go across negative 1, it stays the same. Now we have a positive and we're going across 0. Where did 0 come from? Which term? It came from the 4x. X has an odd power, x to the first. So that means we're going to go through. So the sign is going to change. So I have a positive. So as I go across 0, it changes to a negative. And then now we have a negative and I'm going to go across 1. 1 came from this term, x minus 1 squared, has an even power, so my sign is going to stay the same. So I go across 1. So that is a nice shortcut, because then I only have to do one test point and then just look at the powers of my the terms that gave me my critical numbers. And we're done. So then that means that, well, we're done with the increasing, decreasing part. So we can say f of x is increasing on, where is it increasing? Minus infinity to minus 1 union minus 1 to 0, and is decreasing on 0 to 1 union 1 to infinity. So with this, could we graph the function already? So I know it has to increase, and then our local max here is at x equals 0. But we already know that the y value when x is 0 is y equals 0 also. So when we go here to try to graph it, I can kind of place where my graph is going to be. So I know we're increasing here, but notice this is our only x-intercept. So I can't be coming from down here, because then that means I will have to cross somewhere in here. So my graph can't be here. So my graph is increasing, and so it has to be here. So it increases because I don't have any other x-intercepts. So it has to be there. And then from here, it increases, and then I have a local max at 0. So when I have a local max, we look like a upside down parabola, right? The sad face. So that's what we look like here. So that makes sense with our increasing and decreasing. We increase from -1 to 0, but then decrease from 0 to 1. So then we're looking like a parabola over here, or part of a parabola, right? It's not, this function is not really a parabola. So, and bear with me here, my not so pretty graph. Asymptotes also help guide your graph, because you know we have to grow along the asymptote. So now here, if we cross the asymptote, we should be able to get y equals 2. So when you go to the original function, where's my original function? Here. If you set this function equal to 2 and you're able to solve to get an x value, that means that's where we cross the asymptote. But notice that if I try to solve, these are going to cancel, and I'm going to get 0 equals -2, which is not true. So that means that we don't cross the horizontal asymptote. It is possible to cross a horizontal asymptote. It is not possible to cross a vertical asymptote. The only way that you might see like part of the graph be with a vertical asymptote is if it's a piecewise function and it has been redefined as something else from that asymptote on. All right, and then the last part is this, from 1 to infinity, the function is decreasing. So to decrease, that means the y values are getting smaller. But again, I can't be over here, because that means I will have another x-intercept, but we only had the one x-intercept, 0. So that means to decrease, I will have to decrease this way from the asymptote coming down and then following the horizontal asymptote. And we don't cross the horizontal asymptote because we saw there's no x value when y equals 2. So that looks like the shape of our graph. Now we still need to do concavity to verify. So what we should expect is to see concavity. This is concave up from -infinity to -1, then concave down all the way from -1 to 1, and then concave up again. So if we're wrong, then we'll have to come back and look at our concavity and fix our graph. But oftentimes you can already graph it just based on the increasing and decreasing portion. So let's go for concavity now. So f double prime of x, and recall what was our f prime. So f prime, and so notice I said use this for f double prime because I don't really want to use this one. This one I will have to use a product rule on the bottom, whereas here I don't need it. But rewriting this in the simplified version helps me find my critical numbers better. So sometimes you have to simplify the function further to have it like give you critical numbers better, but you may have to go 1 or 2 steps before simplifying for the second derivative. So negative 4x over x squared minus 1 squared. So that's our first derivative. So let's take the second derivative. So second derivative is we still need the quotient rule. So bottom x squared minus 1 squared times the derivative of the top. So times negative 4 minus the top, negative 4x, times the derivative of the bottom. And so here I need a chain rule. So 2, the inside left alone, times the derivative of the inside, all over the bottom square. So x squared minus 1 square square gives me to the 4th. And then can we simplify further? Can we, and here remember, we don't necessarily want to multiply things out and get it to be really crazy. Think about factoring. What can we factor out? And I can already see that I have a negative 4 and a negative 4 there. So we can take that one out. So let's take a negative 4 out. What else can we take out? We can take out, I see an x squared minus 1 and an x squared minus 1 squared. So we can take out one of those. So let's take x squared minus 1 out. And then what are we left with? We only took one of those out and we had square. So that means we're left with one of them. We took out the negative 4, so that's no longer there. So minus, we took out this negative 4, so that x is there, times 2. We took that one out, but I still have that 2x, all over x squared minus 1 to the 4th power. And now we can get rid of that one with one of those and continue to simplify. So I'll have x squared minus 1 minus, what's this, 4x squared over x squared minus 1 to the 3rd. And can we simplify further? Minus 4, what's inside here? X squared minus 4x squared, so that's negative 3x squared minus 1 over x squared minus 1 cubed. And take out another negative from there. Both of those are negative, so take that negative out. And so when you take a negative 1 out, that becomes a positive. So I'm going to have positive 4 times 3x squared plus 1. Taking the negative out. All over x squared minus 1 cubed. And so when I set this equal to 0, notice that the numerator is never 0. This is an irreducible quadratic, meaning you can't factor it or do anything with it. So this is never 0. And so the only critical numbers or candidates of inflection point are 1 and negative 1, right? So f double prime of x is never 0, but f double prime is undefined at x equals negative 1 and 1. So that's kind of making sense with what we thought. So let's put our candidates for inflection points here, and same thing, we're checking now the second derivative and seeing what does the function do. So pick a test point. Let's say x equals 0. We'll use our power trick shortcut to do this one. So when x is 0, what do you get? 0, top is positive 4 times 1. So when x is 0, you're going to have, for the second derivative, positive divided by 0 minus 1 is negative 1, cube is negative. So positive divided by negative is negative. So our second derivative is negative when x is 0. So in the middle interval, which says what about the function? When the second derivative is negative, the function is concave down, so sad face. And now let's use our trick for the powers. So as I go across 1, where did 1 come from? So I guess we should probably factor this out the way we did with the first derivative. So x plus 1 cube and x minus 1 cube. So as I go across positive 1, which term gave me x equals 1? It was the x minus 1. So that is cube, so odd power. So I have a negative. So that means that the sign is going to change. So that means now the function is going to be concave up. And same thing the other way. As I go across negative 1, I'm working with the negative. As I go across negative 1, which term gave me negative 1? The x plus 1 cube, right? When you set this equal to 0, x plus 1 equals 0 when x is negative 1. So that's where the negative 1 came from. Is to the third power, odd. So my negative is going to change signs to positive, which means that the function is concave up. If you don't get the shortcut, or if you're like, what is happening? Don't worry about it. You can just keep doing picking test points. Pick a test point from negative infinity to negative 1, negative 1 to 1, and then 1 to infinity, and you should get the same thing. So now I know it's concave up on what intervals? So we can say f, the original function, is concave up on negative infinity to negative 1 and 1 to infinity. And f of x is concave down on negative 1 to 1. And so looking at how we drew our graph earlier, concave up, concave down, and then concave up. So that makes sense. So this is what our graph is looking like. So lots of time, right? So one problem takes forever. So make sure you don't leave your homework to the end for this section, because these problems take a while, because you have to find the intervals of increase, decrease, and concavity, and the homework kind of walks you step by step, so you can't do it all in one single step. Okay, I'm going to use another video to do the second example.